In the last lecture, I alluded to the fact that a system of equations or a vector equation could also be repackaged as a matrix equation, and I'm going to tell you more about that in the following video. But before we do that, we need to have one video devoted to basic operations with matrices, how you write them, how you add them together, and how you multiply them. So that's going to be the focus of this video. So what are the ways that you write matrices and what can you do with them? Well, our matrices are going to be these boxes filled with entries, which are real numbers for us. And the first thing that you can do with matrices is you can add them. And you add them component-wise, but only if those matrices are of the same size, meaning the same dimension. So for example, I can take some matrices A, B, C, and D. A and B are both 2 by 2 matrices, so I can add A and B together. When I add A and B together, I'm going to add the first entry, 1, to the first entry of B, 1, and that gives me the first entry of A plus B, which is 2. The second entry of A and the second entry of B in the first row, giving me a 3. And because of the way that addition works, being component-wise, A plus B is equal to B plus A. So addition of matrices is also commutative. But what if I were to take a matrix C, which is 2 by 1, and a matrix D, which is 2 by 3? Well, I cannot add C and D together, nor can I add D to A or B or add C to A or B, because these matrices are of different sizes, different dimensions. The next operation I want to discuss is scalar multiplication. And scalar multiplication with matrices works just like it does with vectors in the sense that every entry of a matrix will be multiplied by the scalar. So let's look at another little example. Now I'm going to have A and B, and these are both 3 by 3 matrices. Let's take a look at 5A. This is scalar 5 times matrix A. And the effect of scalar multiplying A by 5 is that every single entry inside the matrix gets multiplied by 5. You can also multiply by -1. That's going to give me minus B. And I've taken all of these entries of B, 1, 1, 2, for example, in the first row, and they all become negative here in the second row, on the first row of minus B. So with scalar multiplication and matrix addition, I can take a linear combination of matrices, much like what I do with vectors. A minus B in particular is an example where I have A plus minus B. So I would be taking the matrix A and adding it to the matrix minus B, producing another 3 by 3 matrix, A minus B. You'll remember from our discussion about vectors that there was a natural question, can you multiply vectors together? And the answer was a yes, but when you multiply them in the sense of taking the dot product, you do not get another vector, you get a number. This is where matrices are going to diverge from vectors a bit. Matrices can be multiplied together with matrix multiplication, but we're going to need to be careful about the dimension, and we're going to want to define it with care as well. Let me just write down what the rule is. Yes, matrices can be multiplied together. If I have a matrix A with entries Aij and a matrix B with entries Bij, then I can multiply them together as long as A is an m by n matrix and B is an n by p matrix. And the result of doing so is going to be a new matrix that I call AB, which is going to turn out to be an m by p matrix. So you can see that I've color-coded the dimensions a bit. The requirement is that if A has m rows and n columns, then B better have n rows. And then the dimensions of what I end up with, m by p, come from the m and the p in A and B. The entries of this product matrix are what I'm calling Cij. And each one of these Cij's can be defined by the following summation. If you expand out this summation, then you see that you'll have AI1 times B1j plus AI2 times B2j, and so on and so forth. We're going to spend a bit of time unpacking this definition, and what we're going to see is that this entry right here, Cij, is given by a very particular dot product that we find from taking a single row out of A and a single column out of B, and then dot producting those two rows and columns together as vectors. So let's break this down. We're going to warm up with a specific type of matrix times matrix, and that's going to be a matrix times a vector. If you think about it, a vector is an n by 1 matrix. So we're going to look at the special case of this matrix A, 1, 2, 3, 4, and we're going to multiply it times the vector x, which is 5 and 6. The dimensions of what we're looking at here, by the way, are 2 by 2 and 2 by 1. So if I'm matching dimensions, these agree, which means I can multiply these together, and then what I'm going to end up with is a 2 by 1. So my expected outcome is going to be a 2 by 1 matrix, aka a vector, in R2. So how exactly is this going to work for this particular example? All right, so AX, matrix A times vector X, is 1, 2, 3, 4 times the column vector 5, 6. And I'm going to work out what each of these entries are. The first entry is going to be given by 1 times 5 plus 2 times 6. Those will add together to give me a number. And the second entry is going to be given by 3 times 5 plus 4 times 6. You can add up these numbers, and that's going to work out to be 17 and 39. So what pattern am I actually following here? Let's look at the first entry and highlight what's going on. I'm taking the first row of A, and I'm taking the column vector 5, 6, and I dot product them together. The dot product of two vectors means I multiply together the first two entries, and I multiply together the second two entries, and I add them up. So this is a dot product that I'm really seeing here. And I do the same thing to get the second entry, except I'm going to be using the second row from A. So when I do the second entry, I'll be taking the row 3, 4, and then repeating using 5, 6. And that's going to give me 3 times 5 plus 4 times 6. All right, so that is how I produce matrix times vector. And I see that each of these is obtained as a dot product. Each of these entries is a dot product of a row vector and a column vector. Let me now write down the same thing with generic entries that are not specific to any particular example. So I'll size this down a little bit and then write down a 2 by 2 matrix times a generic vector. All right, so generically I would be looking at something like this. AX would be a matrix with entries A11, A12, A21, and A22. The vector that I multiply is X1, X2. And this gives me A11 times X1 plus A12 times X2. And then here I would have A21 times X1 plus A22 times X2. And these are dot products. So another way I could write this is that I'm taking row 1 dotted with this vector x, and row 2, thought of as a vector, dotted with the vector x. This funny summation that I originally wrote down is just a very fancy and concise way of writing down these dot products. So let's now move towards a matrix B and think about what A times B is going to look like. Remember, a matrix B is a collection of column vectors. The first column is a vector, the second column is a vector, and the third column is a vector for this matrix B. And I want to call them column vectors B1, B2, and B3. So one way that you can think about matrix multiplication is to say that this is a matrix times a vector just repeated for every column vector. So I'll write that down. Matrix times vector, giving us a vector, but repeated for every column vector. A times B can now be written as A times the matrix comprised out of the three column vectors B1, B2, B3, which is then A times B1, A times B2, and A times B3, each of these being on its own a vector. And I line up these three vectors and I get the new matrix A times B. So let's look at a really specific and color-coded example. So my matrix A is going to be the one highlighted in green and blue. And my matrix B is going to be highlighted here in pink and yellow. So I am going to do A times the first column vector of B first. And that means I'm going to be taking row 1 times the pink column. And that gives me the first dot product. Then I'm going to take row 2 times the pink column. And that gives me the next entry. I've done this once, matrix times vector, and that gives me the first column vector of the product, AB. When you work out these little dot products, you see that they're the numbers 4 and 10. Now I'm going to repeat that process, but using the yellow second column vector of B. I take row dotted with column, and then I take row dotted with column again. This gives me these two dot products, which are these two numbers, -2 and -4. The second line in what I've written down here is just another way of rewriting the exact same thing. I'm taking a big matrix that's formed out of matrix times vector, giving me, of course, these exact same numbers. Thinking about matrix multiplication as dot product in this way really explains to us why we have this dimensionality constraint. So let's think about that. The dimensions, in order to have matrix multiplication, recall that the dimensions have got to match up in the right way, in the sense that if you have an m by n matrix, you've got to be multiplying times an n by p matrix for this to make sense. This and this have to agree. That's because when you carry out matrix multiplication, you're doing a row dotted with a column. And dot products only make sense if the vectors have the same number of entries in them. So these have got to have the same dimensions in the sense that the number of columns of A better agree with the number of rows of B.